ds, the mass per unit surface area, would be sigma. And so to calculate the total mass, we integrate sigma over the surface area, which in this case, since my sigma is theta, gives us, and ds, remember, is r squared d omega, which integrates, but the theta is here, so it's not just a pure d omega. So it's r squared theta times sine phi d theta. And you do the integral, and you get 4 pi squared r squared. And so we can also do things like calculate the average of z squared over a circular cylinder. So what would we do? The average over a surface would be what? You calculate the surface integral, the scalar surface integral, which just means you take the function and integrate over the ds without the vector on it, right? And then you divide by the surface area. That gives you the average of a function over a surface. We also have that concept again. You could calculate the center of mass of a surface, or the moment of inertia of a surface, just the same. Oh, look, here's the center of mass of a cone. Well, centroid. So what's a centroid? It's assuming the mass density is 1. You know, it's the same, it's constant. Cone pi over 4. So you can use symmetry, I think here. Wait a minute, I do something weird, don't I? Seems like I should have x bar and y bar both be 0. Oh, yeah, I do. Curse the cursor. Stupid cursor. Why, you know, this is a $1,000 computer. Like, why is there an hourglass there? Why does it have to think about this? We should really be at the point where when you move a cursor on a computer in 2017, it needs to go hourglass. Let me think about what I'm doing. That's sad. That's sad, Microsoft. That's just sad. Sad, 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 sad. I'm sorry. Where's my hover car, et cetera, et cetera, et cetera? Comments about the future. It's coming? I mean, maybe we should all have our own personal, like, drone, right? Just go sit in your, I mean, have you ever looked up the YouTube video of the guy? What's happening to my voice? Wow.
You sounded like really excited about it.
So there's this YouTube video, this guy who's taken, like, I don't know, 100 of these little gasoline-powered drones and built some kind of rig where they're all computer controlled together. And so he just switches them all on, and he's like in the seat, and it gets about like 3 feet off the ground. It's so stupidly dangerous. Like, it's fantastic. Anyway.
I have a helicopter.
You should do that for your engineering. Like some of you guys, you always come to me like, "We need ideas for our engineering projects," and I always suggest things, and you always tell me that they're not legal, because I want things like a workaround for like the security, like the badge readers. Like I just want some sort of thing that can just disable those. That would be like one of the things I ask for. What's that? Ooh.
I think
for example,
what he needs is a spoofer that will spoof any badge you want.
Something like that. Yes.
See,
But I'm generally told that my ideas are not, like they're looking for legal things for their projects. So yeah I don't know. It's not ethical doesn't mean it's not legal. Spoken like a businessman. Very good. Yes. Or politician. I'm not sure. Let's see here. Let's see.
Well, you know, the line's getting blurry these days.
The line's getting blurry. Yeah. So this is very good. Anyway, so the z-bar, the coordinate for the centroid in the z, what do? I have to, what is this? So we're supposed to integrate z ds, right? What is ds here? I can't read my own. ds is rho over 2 d theta d, rho over root 2, right? But the thing is, z is also rho over root 2 here, right? Because z is equal to, where is this? I can't find where I've written anything, but anyway, you plug in the parameterization for the cone, and it gives you this. And then part of this is the ds, and you integrate, and you get that. You can also calculate the moment of inertia. That would be the integral of r squared delta ds. Now, here I'm talking, I assume that delta is 1, right? But you could do that. Now, let me put this away here. And So tomorrow, so I have examples of flux integrals. We could look at those. If you have a question about homework tomorrow, we should have time for that. But otherwise, I will go on to Stokes' theorem tomorrow. So you're so stoked. You're stoked. You're so guys. Okay, so in the time that remains, I suggest we calculate the moment of inertia for a spherical shell with mass m. We have calculated, what's that? No? We've calculated the moment of inertia for a solid sphere before. What did it work out to? Something? It had a fifth in it.
I left my notes when I read back.
I want to say 2/5 mr squared. So for solid sphere, I 2/5 mr squared, I think is what we worked out. So suppose you have a spherical shell. So sometimes we draw these things with like a little cutaway so you can see it's a shell, right? So it's a shell. So again, shell, let's suppose that total mass m, radius r. I want to calculate the moment of inertia. So the moment of inertia about the z-axis here, what that is it's the integral over the sphere of radius r, really spherical shell, of course, but of what? Of delta. Well, before this is the r squared dm. Now, what that actually looks like, of course, and I don't know, I feel like I should have a double integral here, but fine, whatever. So that's rho squared delta ds. So if this delta is constant, right? So delta is equal to the mass per unit volume. Not volume here, what? Yeah. Or we use big S for that. Curvy area. Now, if that's constant, we can already relate R and M because we know that the total mass is M, right? And what's the total surface area of a sphere? We worked this out yesterday. 4 pi r squared, right? So to calculate the moment of inertia for a spherical shell, I should integrate over the sphere, the scalar surface integral of r squared. And my delta is actually what? It's actually m over 4 pi r squared, right? And then, of course, ds. Now, okay, so let's do that. This is m over 4 pi r squared. And then I have the integral from 0 to 2 pi, the integral from 0 to pi of r squared. Now, r squared is, okay, so at this point I need to, we're using what we did yesterday. Yesterday we worked out that ds was r squared sine phi, d theta, where we're using what, x, well, we're using phi and theta as parameters for the sphere, right? So that's the thing we spent all of yesterday on, all right? Now, this r is the cylindrical radius, right? So what's the, r is equal to, what is it? Rho sine phi, right? But we're on the sphere of radius big R. So that's where rho is equal to r. So this r squared becomes big R squared sine squared phi. That's my r squared. And then, of course, my ds gives me r squared, what? Sine phi d phi d theta. Now, thankfully, some of these r squareds cancel, but we've got m r squared over 4 pi, and then I have to do what? I have to integrate from 0 to 2 pi my, my d theta, and I have to integrate from 0 to pi, I believe, sine cubed phi d phi. So that gives me m r squared over 4 pi times 2 pi times 4/3, also known as, what is that? The 4's cancel, the pi's cancel. What am I left with here? 2/3 mr squared, yeah. Have you guys used that in Physics 231 yet this semester? Did they ask, like, what's the kinetic energy of a rotating spherical shell that you'd need this for?
They just gave us a big long list of formulas for random.
Right.
things.
I guess my question to you is, does it make sense that the moment of inertia here is larger than that one? This is about 0.4. That's about 0.67 mr squared. Well, it makes sense. Like, for a given rotational speed, there's more mass further away from the center of rotation for the spherical shell as opposed to the solid sphere, right? The solid sphere has got some mass close to the axis of rotation, which has less rotational kinetic energy.
Although presumably, for equivalent solid spheres and shells, solid spheres are going to have much more mass.
Well, I said
If they have the same mass, then you've got quite a dense little shell there.
I said the same mass. I mean, so but yes, if it was the same shape and the same material, then of course the solid would have more. Yeah.
Well, but the shell has.
This integral is one of our favorite integrals that appeared in your last test, right? It actually was in the moment of inertia calculation of as it happens, the final problem of the test. That's how I knew that was 4/3, is because I worked it out in the last month or so, and I happen to remember it because some of you got it wrong, which made it a memorable experience for me.
So I wish we would go over stuff like this again.
So the good news here is, guys, is if you did bad on the last test, and that's many of you, there is a natural redundancy in this course, right? In fact, that's the beautiful thing about the last part of this course, is it has everything in it. It's got geometry, it's got the parameterizations, it's got the coordinate systems, it's got partial differentiation, it's got integration of area integrals, it's got volume integrals, it's got just about everything we've done this semester, right? Some instructors just test this part of the course for the final exam. Should I do that? I'm just kidding. No. I'm not going to do that. But it's conceivable to do that because it gets everything. Anyway, I shut up. I'll see you tomorrow. Wait a minute. Of course, we're not meeting tomorrow because it's Good Friday, right? No one would have school on Good Friday.
It's Good Monday now.
That's Good Monday, yes.
Wait, so no test?